in modern algebra, there are certain theorems that typically don't prove those results in class because, well, the proofs don't use techniques that we need for homework, or the techniques don't really demonstrate things that are native to that subject. And so there's a whole cluster of these sorts of theorems that their proofs are proof by induction. The proofs are kind of tedious. And when you get done, I don't think you've really learned anything that at least is kind of like abstract algebra related. And so an example of one of these theorems is that if you have associativity among three things, say A, B, C, then you have associativity among n things. And so when we have, say, a group or a ring or whatever algebraic object we're working with, we will demand that associativity holds for A, B, C, and then we don't write parentheses when we have expressions involving not just three, but arbitrarily many symbols. Okay, so how does one prove this? Well, the proof is by induction. Okay. And so first, I'll just note that if you have a single symbol or two symbols, we don't need parentheses anyway. So there's no product, or there's just a single product there. You don't need parentheses to distinguish. When we have three things, there's two distinct ways of parenthesizing, and our hypothesis will assert that these are the same. And let's call this this expression here left parenthesized. And maybe for this video purpose, we'll call that LP. And so if we take an expression A1, A2, A3, etc., all the way up to AN, and we've moved all the parentheses over to the left, let's call that a left parenthesized expression. Okay, and what I want to do to begin with is to show that an arbitrary expression can be left parenthesized if we have this assumption just for triples of things. Okay, and then once we have that, we'll finish up our proof that we don't need parentheses at all. Okay, so here we go. We're going to go by induction. So for an inductive proof, we need our base case. There we go. There's our base case with three things. And so let's now make an inductive hypothesis. Let's assume. So we'll suppose that given any expression involving, let's say, k less than n elements, say A1 through AK, this expression can be left parenthesized. Okay, so that's our inductive hypothesis. By the way, we're going to assume that n is at least 3. Okay, and we already did our base case for n equals 3. And amongst this, if k is 1, we don't need parentheses. We'll assume that's kind of vacuously left parenthesized. And if k is 2, again, the same thing. We'll just put parentheses around if we need to. Okay, and then now let's suppose that x is some parenthesized expression involving the symbols A1 through AN. Okay, so we've taken a product A1 through AN, we've parenthesized it, and what I want to show is that it can be re-parenthesized so that it's left parenthesized. Okay, well, imagine we take X. There is an outermost set of parentheses, and so X ultimately either looks like A, B, C, or it looks like A quantity BC, right? The outermost parentheses either start at the far left and then end somewhere in the middle of that expression, or they end at the far right, starting somewhere in that expression. So whichever case that is, whichever x is, we know that those things are equal because of our hypothesis that we can move parentheses around three things. Also in this, since our expression x involves at least three symbols, I'll make a note that A, B, and C each have at least one thing in them. That's our setup. Okay. So in any case, we have that now that x can be rewritten as something like this: D and some expression in parentheses C. And let's focus on C. I want to tackle this guy first. And we'll say, note, since D involves at least two symbols, two elements, C involves less than n symbols. So C is something that we could apply our inductive hypothesis to. Okay. Now there's sort of like three cases to consider. Kind of case one is that C is just a singleton, right? C is just an, the last guy by himself. Well, in that case, we have that x looks like in parentheses something an, and that's our D. Let's just relabel that to be E. Okay, so there we go. Now I'm going to present two more cases. In each case, in the end, I'm going to get it to look like this. Okay, so case two, our expression could just involve the last two symbols, say an minus 1 and an. So what does x look like? X looks like D in parentheses and then an minus 1 an in parentheses. That's what x looks like. Well, we can use our hypothesis and shift these parentheses over. And if we do that, we have an expression that's some stuff involving n minus 1 symbols and then an at the end. And so once again, we have some kind of expression and then an right at the end. Okay. Now for case three, right? Let's look at that. So for case three, we have that C is an expression involving, let's say, ak plus 1 all the way up through an, okay, where, n, where k is, let's see, n minus k is at least 3, okay? So there's n minus k symbols involved here, and we have at least 3 now, okay, because we've taken care of the case where we just had 1 or 2. All right, well, by our inductive hypothesis, since n minus k is smaller than n, and it's at least 3, we have that C can be left parenthesized. And so in particular, we have that C can be written as ak plus 1 in parentheses, then ak plus 2, etc., all the way up to an. So we can left parenthesize C. But importantly, what we have is that our expression x, remember it was dc here, well, this now looks like d, and then the expression I have written up here right? And I can move parentheses over using our regular old hypothesis. I have D, and I have what the left parenthesized version of C. Well, all the way up through the next to last guy, and then we have AN there. So I take this outermost parentheses and just move it right over, right? There's an AN minus 1 right there. Okay. So if you look at this expression, once again, this is some kind of expression E involving the first n minus 1 symbols, and then AN right at the end. Okay, so in all cases, whether we just had one thing in C, two things in C, or three or more things in C, we can always rewrite X in this way. Okay, well then, we call on our inductive hypothesis. Once again, by our inductive hypothesis, E can be left parenthesized, right? Because E, it has n minus 1 symbols in it. That's shorter than n. So our inductive hypothesis can be applied to that. And so we have that X, which was equal to E with AN tacked on the end. Well, E can be left parenthesized. And so it looks like A1, A2, A3, all the way up to AN minus 1. There's E, and then AN at the end. So here's E left parenthesized, and then we have that. So what have we just shown? We have just shown by induction, any expression X can be re-parenthesized to be left parenthesized. Okay. Now, we can finish up our proof by saying, consider, suppose that X and Y are parenthesized expressions involving A1 through AN, okay? And so we know that by our proof, we have that X can be left parenthesized so that it looks like A1, A2, A3, all the way up to AN. But we can also apply our result to Y. Y can be left parenthesized, so it's equal to the left parenthesized version, and therefore by transitivity, X and Y are equal to each other. Therefore, in all cases, we don't need parentheses anymore. So if you have parentheses for triples, if you have associativity for triples, you have associativity for n things. Now, as an addendum to this, I'll point out that there are some algebraic systems where you don't have associativity. In fact, there's a lot of important algebra done, say like Lie algebras are a good example of a kind of product that isn't associative. The cross product is an example of this. You may run into that in a multivariable calculus course. There are also some weakenings of associativity that show up occasionally. And just so we'll throw these in here. We have an alternative algebra would be where you have associativity, but only when there's two or less distinct things involved. So alternation, you might write, let's put it, you could put B first. So for all A and B, you could put B first. You could put B in the middle. I don't know why that's so hard. Or you can put B at the end. And if you assume that these things hold, right? So that's associativity among triples, but where you're only involving up to two distinct symbols, that's an alternative. That an algebra whose multiplication works that way, that would be an alternative algebra. A weakening of that is power associative. Power associative is where you just have this for a single symbol. So that would be just for strings of A. And we could apply our result just as well in these cases. Basically the same proof goes through where our A1 through AN now, well, it is the same proof. Our A1 through AN are now either just A's and B's or just A's. And this goes to show that in power associative algebras, if you have a positive power of A, you don't need to write parentheses. You can just write A to the N. You don't have to say how you're computing, say this would be like A cubed. There's no ambiguity, and no matter how you parenthesize, that's always A cubed. You don't get different answers, which, by the way, and there's algebras called, say, Leibniz algebras, where that's not the case. Okay, and those are of interest. Alternative algebras, these are ones where they would be power associative, but also even more so, you could do it with two distinct symbols. Now, are these things important? Yes. Exactly why? Examples of other alternative algebras, like, say, the octonies or something, that sounds like that's a topic for another video.